And good day to you. PTQ Magazine and Digital Refining are pleased to bring you this webinar featuring Sulfur. My name is Ken Mollet. I'll be acting as your facilitator today. And now I'll turn things over to Rahul Khandelwal, Business Segment Leader at Sulfur. Rahul, it's all yours.
Thank you, Ken, for the introduction. The topic of today's webinar is plastics recycling, with a special focus on the chemical recycling category. The webinar has been structured to introduce Sulfur, followed by the market drivers shaping up the plastics recycling area. And then we will focus on our technology portfolio in this particular category. This is a safe harbor statement for legal purposes. Now, Sulfur Chemtech has a diverse footprint. We offer equipment and services which cater for different applications. On the technology and licensing side, we have an extensive portfolio both in the refining as well as petrochemical arena. And we offer these processes as technology licenses, which include any proprietary equipment, catalyst, or chemicals required in the process. We cater to different market segments. Chemicals, this includes acrylic acid, MDI, and it also includes the specialty chemicals area. Renewables, this includes bioplastics like PLA and plastics recycling, which is the focus of today's webinar. Gas and refining, and last but not the least, the water segment. Over here, we offer solutions for industrial wastewater treatment. Now, why has plastic recycling gained so much mainstream attention? Looking at the graphic shown on this slide, approximately 330 million tons per annum of virgin plastics are produced every year, out of which a staggering 260 million tons per annum land as waste plastics. Now, these waste plastics undergo different routes. 25% are incinerated, which lead to greenhouse gas emissions. 40% are landfilled, which are an environmental hazard on their own accord. And 20% are beyond any human control. These are plastics floating on the ocean or scattered on the land masses. Focusing on the recycling rates, only 12% are recycled by mechanical means, and chemical recycling accounts for a minuscule less than 1%. Thus, one can see plastics recycling has become an environmental necessity. Now, because of its environmental necessity, there are drivers shaping up both at the legislative as well as at the market level. In Europe, the first plastics tax has been put into place, which is 800 euros per ton on the basis of non-recycled plastics. The European Union has imposed this tax on the member countries, but the member countries have been left with their own choice as to what mechanisms they want to implement to promote the plastics recycling. On the market side, different brands are demanding more recycled content. Companies like Coca-Cola, Nestle want more recycled content in their bottles. Now, moving on to the recycling categories. There are two main categories, the mechanical and the chemical recycling. Mechanical recycling dominates, but chemical recycling is picking up steam. And there are differences in both the approaches. In case of mechanical recycling, the plastics feed needs to be quite clean and it needs to be quite sorted. This is because small amounts of polymer dispersed in the matrix of another polymer can cause issues with mechanical recycling. A classic example is small amounts of PVC during the PET processing. Chemical recycling, on the other hand, can accommodate a wide variety of feed, although this feed needs to be sorted only to a certain extent. So that's an advantage chemical recycling brings to the table. Polymer degradation. Now, what happens during the mechanical recycling process is that with every cycle, the properties of the polymer degrade. And there comes a time that the polymer cannot be used for its intended application. Chemical recycling, on the other hand, since the waste plastics are being broken down into hydrocarbon molecules, does not suffer from this polymer degradation limitation. Those hydrocarbon molecules can be fed into downstream polymerization process to produce a polymer which rivals the properties of virgin polymer. greenhouse gas emissions. Now, wherever mechanical recycling can be applied, in other words, the feed is clean and the polymer degradation has not gone to a certain extent, then greenhouse gas emissions for mechanical recycling are the most optimal one. In the case of chemical recycling, the jury is still not out there. There have been different studies done by research institutions as well as organizations which claim that chemical recycling does bring in greenhouse gas emission savings, provided the emissions from incineration are taken into account. Our view with respect to the recycling space is that mechanical recycling will continue to dominate. However, chemical recycling will gain significant market share. And this is what is highlighted on this slide. If one focuses on the graphic on the left-hand side, one can see that the polymer demand is expected to grow at a healthy rate for the next 3 decades. This is because of the population growth that is foreseen in the next 3 decades, and at the same time, the middle class upliftment being seen in developing countries. Focusing on the table on the right, one can see that mechanical recycling will continue to dominate the mix, and it is projected to increase approximately 3 times. However, chemical recycling, which is shown by the red dotted box, will increase at an exponential rate. And this is because of the advantages it brings to the table. Now, what are the different polymer recycling methods? Pyrolysis is when plastics are heated up to certain temperatures, which are typically anywhere from 300 to 400 degrees C in an inert atmosphere, and it can be done thermally or it can be done in the presence of catalyst. When catalyst is used, as one can imagine, the temperatures are relatively lower. Now, in the case of thermal pyrolysis, a broad product slate is obtained. This product slate can start from naphtha to distillate all the way to the heavy fraction. However, in the case of catalytic pyrolysis, a main advantage is that the product slate can be tailored. It can be targeted more towards cyclic, naphthenic, or aromatic molecules, and it depends upon the customization of the operating conditions as well as the catalyst. If pyrolysis is being applied on polystyrene or PMMA, then one obtains a monomer-rich product slate from which styrene or MMA needs to be recovered. Depolymerization. Depolymerization is a method where an external agent is added to break the polymer into the starting monomers. This is what is used for PET chemical recycling or for polycarbides, polyamides, or polyurethanes. A major limitation of this approach is that it can only be applied for condensation polymers. For addition polymers, which form the majority of the plastic spool, this approach cannot be applied. Solvent-based recycling is when a solvent is used to dissolve the waste plastics along with the other contaminants and additives. Thereafter, the contaminants and additives are separated in downstream processes, and the solvent along with the polymer is sent to a separate section for solvent recovery, and the recycled polymer is obtained. Now, what is Sulzer's portfolio in the plastics recycling arena? We have technologies for the PET and the polyamide recycling, wherein we offer expertise for the downstream monomer separation. In the case of polymers or natural fibers, we offer solvent-based recycling processes. For polystyrene or PMMA, we offer styrene/MMA recovery processes for the recovery of the monomer, which comes out of the depolymerization section. And lastly, in the case of mixed plastics, or even in the case of waste tires, we offer know-how and processes for purification and upgradation. Now, we will touch upon each of these segments in the subsequent slides. PET chemical recycling. Over here, we bring in our know-how on the distillation and the crystallization for the separation of the monomers which are obtained from the depolymerization of PET, which can be practiced either by methanolysis or hydrolysis or glycolysis. For the case of polyamide chemical recycling, we offer a hybrid approach downstream of the depolymerization section for the recovery of the caprolactam. We are able to produce the highest grade caprolactam, meeting and exceeding all properties that are required for such a product. A crystallization block is used downstream, and an important function of this crystallization block is to remove impurities which cannot be removed by distillation. Solvent-based recycling. Over here, for the separation of the polymer from the solvent, we offer a unique devo or devolatilization technology. A significant advantage of this technology is that it can be applied over a broad range of viscosity for the solvent and polymer mixture. And one is able to get the solvent levels to very low ppm levels in the recycled polymer. Now, as one can imagine, during solvent recycling, an important criteria is to recover the solvent. Over here, we offer different approaches for the solvent purification as well as for recovery. An example of our industrial activity in this segment is the One Again venture. One Again is a UK-based startup which has developed a process for the recycling of end-of-life textiles. And over here, Sulfur is a major shareholder and is bringing both knowledge as well as equipment know-how for the scale-up of this One Again process to commercial level. Moving on to polystyrene chemical recycling. Now, if one looks at the polystyrene chemical recycling value chain, then the waste polystyrene needs to be sorted from the mixed plastics. Thereafter, it goes to a depolymerization block, which is shown as the green box, and it can be a pyrolytic or a catalytic, or in one particular case, a microwave-based approach. After the green unit operation, a crude styrene-rich oil is obtained, and from here, the styrene monomer needs to be recovered. Now, we have developed a unique configuration for the polystyrene chemical recycling on the purification side. And the reason for the development of this unique scheme is, number one, despite the employment of the state-of-the-art sorting methods, non-styrenic plastics can lead to impurities which can be left in that crude styrene oil, which cannot be removed by conventional distillation. Number two, during the depolymerization process, certain impurities like phenylacetylene or orthoxylene can be produced, which essentially co-boil with styrene. These impurities again cannot be removed by conventional distillation. Thus, there is a need to develop a unique scheme. And this is what we have developed. If one looks downstream of the pyrolysis block, we can offer the full portfolio, starting from the quench section, and then the styrene purification scheme, which is highlighted in the dotted blue box. What we have developed over here is a hybrid approach. We use distillation, which can be divided wall column or a set of two columns, to produce an impure styrene cut. We don't go all the way to 99.7 or 99.8% styrene purity. Rather, we go for 99% purity coming from the distillation block. And we let all the co-boiling and close boiling impurities come along in this impure cut. This impure cut is then fed into a proprietary crystallization block. This is melt crystallization, very simple and robust operation. No centrifuges involved over here. And the elegance of using crystallization over here is that it is able to remove impurities which cannot be removed by distillation. And we have demonstrated with real life samples that we can achieve purities exceeding 99.958% on styrene, and all other impurities, phenylacetylene, xylenes, EB, cumene, to extremely low levels. We in fact exceed the ASTM specs. We have labeled this technology as sure styrene. Now moving on to mixed plastics or waste tire recycling. Again, downstream of the pyrolysis block, we can offer the full portfolio, starting from the quench section. We can offer customized designs for the quench section along with supplying those designs under a skid fabrication approach. Now, what happens with these mixed plastics pyrolysis oils is that because of the nature of the feedstock, certain contaminants will invariably present in these pyrolysis oils. These are sulfur species, nitrogen species, oxygenates, high level of olefins. Now, these contaminants need to be removed before these oils can be used for downstream valorization. And this is where we offer a hydrotreating based approach. And our hydrotreating technology is based on a unique concept, which will be talked in subsequent slides. And that concept relies on liquid recycle. This technology is called max flux, and we project anywhere from 30 to 40% capital as well as operating expense savings, and the ability to remove all the contaminants which were mentioned earlier. Now, once these contaminants are removed, this pyrolysis oil generally will go through a distillation step from which different cuts would be obtained to go to relevant destinations. Now, we at Sulzer Chemtech have experience in dealing with the separation of these pyrolysis oils. Sulzer Chemtech in 2020 put into operation a distillation skid for a reputed recycler in Europe called Quantafuel. The capacity of the skid is approximately 20 kTA. Further downstream of the fractionation, we can also offer processes. For example, if a catalytic pyrolysis approach has been used for mixed plastics, then these oils can contain a decent amount of aromatic molecules. And we are one of the leading licensors for the aromatic extraction technology. So we can recover those molecules. The heavy end of these pyrolysis oils contain quite a bit of waxes, and we have technologies to recover waxes from this fraction. Now, what is max flux? This is the hydrotreating technology which was mentioned in the earlier slide. Now, typically, if one looks at the carbon range of these pyrolysis oils, then a conventional hydrotreating approach would involve a trickle bed reactor. Now, in a trickle bed reactor, you have a vapor recycle because one needs to recover the hydrogen in the process. Now, because you have a vapor recycle, the hydrogen needs to jump from the gas phase to the liquid phase before it can start participating in hydrotreating reactions. And as one can see, there's a mass transfer limitation involved. What is done differently in max flux is that instead of a vapor recycle, we have a liquid recycle. And this brings in significant process as well as economic benefits, which are highlighted in the next slide. First and foremost, the mass transfer limitation goes away. Secondly, since there is no vapor recycle loop, all high pressure equipment like recycle gas compressors, high pressure amine contactors go away from that scheme. And this brings in significant capital savings. There is lower operating expense, and this is predominantly because of the fact that the vapor compression power of the recycle gas compressor has been replaced with the liquid compression power in case of max flux. The other operating expense savings comes from the fact that since the reactor outlet is recycled directly back to the feed, there is no need for a feed effluent exchanger. And thereby, any heat loss associated with that feed effluent exchanger goes away from the picture. Last but not the least, one of the main limitations of a trickle bed system is that because hydrogen is jumping from the gas phase to the liquid phase, invariably there will be two-phase formation in the reactor. Now, wherever you have two phases, there will be hotspots. Wherever there are hotspots, there will be cracking. And wherever there is cracking, not only it will decrease the yield of the product, but most importantly, it will decrease the life of the catalyst because of coking. In case of max flux, since it's based on a liquid recycle concept, the reactor always operates liquid full. And thus all these limitations go away from the picture. Now, max flux as a technology has been deployed for different refinery applications, starting from naphtha all the way to atmospheric residue. This is what the process scheme looks like. As one can see, there is no vapor recycle loop, and the reactor outlet is recycled directly back to the feed. These are the main equipment differences between the conventional trickle bed and the max flux scheme. As one can see in the conventional scheme, there is quite a bit of high pressure equipment like recycle gas compressors or amine contactors, which lead to capital investment in that scheme. In case of max flux, all this equipment goes away. There is addition of two equipment. One is a cold low pressure separator, which is a minor contribution to the capex, and the other is a critical piece of equipment, which is the reactor circulation pump. Thus, in summary, the main advantage max flux brings to the table for the hydrotreatment of these pyrolysis oils is the capital savings. And these capital savings are of special emphasis for the plastics recycling area. This is because the throughputs which are experienced in the refinery or petrochemical sector are not seen in the plastics recycling space. So an economical solution is required. Operating savings, as was explained in earlier slide, these also come into the picture, along with the other process benefits of increased catalyst life and less cracking. Now shifting gears to a different topic. One of the main questions which is being looked into in the industry is that how the pyrolysis oil obtained from mixed plastics, which is the largest category in plastics recycling, should be valorized. Now there are predominantly two different routes. One is the refinery route. And over here, one can leverage upon a lot of existing infrastructure, like bottom of the barrel units or FCC. However, one needs to pay special attention to the contaminants that are present in these pyrolysis oils so that these contaminants don't affect the performance of these units. In general, we believe there will be a blend wall limitation of anywhere from 5 to 10% of co-processing these pyrolysis oils along with the fossil feedstock in these bottom of the barrel units. Another main criteria that needs to be taken into account is that the production profile of the overall unit shouldn't be affected because of this small amount of pyrolysis oil addition. In other words, one does not want a 50,000 barrels per day FCC units profile to be affected just because 1,000 or 2,000 barrels per day of plastics pyrolysis oil need to be co-processed. Now, one limitation of the refinery route is that one is, generally speaking, going on the fuel side rather than the petrochemical side. Thus, the circularity in the plastics life cycle is not being established. Now, this statement is not entirely true because even in some of the bottom of the barrel units, you can produce olefinic streams, which can be used for downstream polymerization, but predominantly the statement holds. Now, with the exception of one particular configuration, this is the refinery petrochemical integrated complex. Such complexes are best positioned for the valorization of these plastics oil because relevant cuts can be sent to units on either side. Now moving on to steam cracker. And this is an area which we are seeing getting quite a bit of attention of co-processing these pyrolysis oils as a cracker feedstock. And the reasoning is quite simple. Over here, one can establish the plastic circularity. However, before these plastics oil can be co-processed, as was explained in earlier slides, they contain contaminants which need to be removed. And over here, we advocate hydrotreating as an approach. Now there are some market approaches based on adsorbents or scavengers, but we don't believe that those approaches are robust enough. If these plastic recycling increase in scales in the future, as well as those approaches can only work for certain level of contaminants which can be present in the mixed plastics. Hydrotreating, on the other hand, even though it involves more capex, is a much more robust solution. And over here, we offer max flux as a solution. And the capital savings of max flux are of special appeal just because of the scales which are seen in this arena. Now, another limitation which needs to be taken into account is the end point of the pyrolysis oil. Now, some cracker can accept endpoints all the way to 350 or 400 degrees C. However, there are still some old crackers out there which can accept endpoints only till 200 degrees C. In this case, a significant fraction of the pyrolysis oil, depending upon the mixed plastics used in the upstream process, can go unutilized or it needs to be sent to a different destination. Now, in summary, plastic recycling, as was showcased earlier, has become an environmental necessity. It's no longer a fashion. This has become the need for today. There are activities being taken both at the government level as well as at the market level, but these activities need to step up to increase the recycling rates. Mechanical recycling will dominate, as was explained earlier, but chemical recycling, because of the advantages it brings to the table, will gain significant share. We at Sulzer can offer a broad range of solutions, starting from equipment all the way to process know-how for different recycling categories, as has been shown on this slide. With that, I conclude my presentation, and I would be happy to answer any questions. Thank you.
Wonderful. Thank you, Rahul. I'm going to invite you to turn your camera on. Let's shift our display a little bit here and put ourselves nice and large. All right, we're seeing you and hearing you. We have a lot of questions that have come in, and I'm just going to start rolling through them, and we'll see how many we can get to. And I'm going to start right at the top, Rahul, with a question that came in when you were just talking about the different types of recycling in the industry. If we currently have around 12% recycling through mechanical recycling, and you say that it's going to continue to dominate, even if it goes up to 30%, that's not really domination, is it? How do you reconcile those figures?
So that's a good question. What was meant when we said that it's going to dominate? It's going to dominate the recycling matrix. Even 30% from a broader perspective, as has been rightly commented, it's not domination, and these figures should even go higher if the world really needs to deal with the issue of these waste plastics. What we foresee is that both mechanical recycling and chemical recycling will go neck to neck with regards to technology development, and there will come a time when both of them would be at equilibrium. That equilibrium will keep on shifting. But mechanical recycling, just because of its low economics, low relative capital investment, will continue to dominate the recycling matrix. That was meant by the question.
Okay, great. Let's move on to a question asking about gasification. Would you not consider gasification a chemical recycling pathway because there are no commercial applications or some other reason?
So that's a good question. Gasification indeed is a chemical recycling pathway. In fact, apart from gasification, you also have in situ hydrogenation. Plastic gasification, as one can imagine, up till now, there has been no commercial units in operation. There have been reports of one demo unit being put in place by a company somewhere in Canada, but this has not gone to the commercial level. There are both advantages and disadvantages associated with this approach, and we believe it would take a little bit of more time to reach commercial maturity. Thermal pyrolysis or catalytic pyrolysis will gain commercial maturity faster.
All right, next question. Where can the polymer oil coming from pyrolysis be fed in petrochemical industry? A steam cracker or somewhere else to produce a monomer?
So this question was addressed towards the end of my presentation. We specifically put together a slide to address this question. So the emerging trend we are seeing, and this trend we are seeing more on the European side than on the US side, is to co-process these pyrolysis oils as cracker feedstock. And one of the main reasons the trend is picking up in Europe is because most of the crackers over there are naphtha crackers. While in the US, a lot of these crackers got revamped or retrofitted to ethane cracking. So, but still, naphtha cracking does happen in the US. It's not completely gone. So if you want to utilize it on the petrochemical side, it needs to be co-processed as a cracker feedstock. However, as was mentioned, certain contaminants need to be removed so that the downstream units on the cracker don't get affected.
All right. Now I'm going to move to a question about recovery of styrene with the SURE styrene process connected to pyrolysis. Starting from the PS waste to styrene UHP, what's the recovery like?
So depending upon the pyrolysis process and as well as the nature of waste polystyrene that was fed and the grades of waste polystyrene that were fed to the upstream pyrolysis process, the styrene yield starting from the waste till the crude styrene oil, once again I would repeat, till the crude styrene oil, is anywhere from 50 to 70%. Now, starting from that crude styrene oil all the way to the final styrene monomer, you can go as recovery as high as approximately upwards of more than 96 to 97%. So those are the two different yields for the two different pathways or the value chain.
Okay, I'm going to keep looking through questions where they're still coming in strong. Can depolymerization be applied to addition type polymers? And if not, why not?
The reason depolymerization cannot be applied for addition polymers is because when you add the external agent for breaking the chains, they don't go back to the respective monomers or oligomers. Condensation polymers are essentially polymers which are formed when you react two different type of monomers or oligomers or intermediates to form that condensation polymer. Addition polymer have a different production pathway. So when you're adding that agent, they don't break down into those respective monomers. So that's one of the main limitations.
Okay, let's see here. Styrene monomers have a very high tendency to polymerize. How would depolymerization or crystallization be controlled to ensure styrene does not polymerize unintentionally? Does it need constant heat input, special tolerances on fabrications of equipment to avoid sharp edges, for example?
That's a very good question. And this question, in a way, highlights one of our main advantages of the sure styrene process, as opposed to the conventional distillation method. Since we are using crystallization at the back end, and we call it the hybrid scheme, and crystallization operates under cryogenic conditions. I mean, the temperatures are as low as -40 or -50 degrees C. The tendency of styrene to polymerize goes down drastically. I mean, there are literally no fouling or polymerization issues by using crystallization at the back end. And at the same time, you are able to remove all those impurities which you cannot remove by distillation. So that's one of the main advantages our scheme can bring to the table.
Okay, we had a couple of questions about catalysts. Does Sulfur have its own HT catalyst for max flux, or can it work with any HT catalyst?
So we don't have a hydrotreating catalyst of our own. However, we can what we do is we explore the optimal hydrotreating catalyst in the max flux process configuration via pilot trials, and then that catalyst becomes a source of supply from our side. That catalyst can be sourced from different established catalyst vendors.
And is there a maximum level of impurities that are allowed by the catalyst?
So the level of impurities allowed by the catalyst are pretty much the same which you would see for any hydrotreating application. One needs to be careful, specifically referring to these pyrolysis oils, one needs to be careful about the metals content. One needs to be careful about silicon or phosphorus, because silicon or phosphorus are used as additives during the plastics production process. One needs to be careful about arsenic and other kind of impurities. So the same level of poisons which need to be looked into carefully in hydrotreating, it's the same application over here. The ranges are different. That's it.
All right. Do you happen to know off the top of your head the operating pressure of max flux?
So there is no fixed answer for this question. The operating pressure depends a lot upon the type of the pyrolysis oil, as well as what you are trying to achieve by the mass flux process. Only hydrotreating, or you even want to go for the hydrocracking? This I have seen one of the questions being posted later on. However, generally speaking, based on a real life testing we have done on these pyrolysis oils, we project anywhere from 50 to 65 bar gauge as operating pressures.
In a max flux reactor, what's done with the unreacted H2? Is it not recycled? Is it recycled after changing phase?
It's not recycled. It goes away with the off gas.
All right. Would the use of pyrolysis and polymer oil as feedstock in the petrochemical industry cause metallurgy impacts on our equipment?
That's a good question, and it was partly addressed during my last slide in the presentation. So because of the kind of contaminants that are present in these pyrolysis oils, and I'm referring to chlorines or any other halogens, oxygenates or sulfur or nitrogen species, one needs to be careful about the metallurgy impact these contaminants can have on the downstream processing. And it is actually one of the main reasons why you need some sort of a purification or upgradation step. It can be scavenger or adsorbents, or as we advocate, hydrotreating, because it's much more robust for this application. But once you remove those contaminants, then the limitation on the downstream metallurgy go away.
All right, I'm going to make this a little bit more generic than the person asked for. Looking at maximum feed concentrations of different elements, where can people find those?
So there is no fixed answer on the maximum feed contamination levels. I mean, nitrogen levels as high as 1,000 or even 2,000 ppm can be dealt with. On the chlorine, a lot of the chlorine can be dealt with within the max flux hydroprocessing scheme. However, if the chlorine content goes higher, we may even put an external chlorine removal unit block upstream of the max flux process. So there are design ways and technologies to deal with these kind of contaminations. In a very big picture, the way to look at the system is the kind of design measures one would employ in conventional refinery processes, where also one deals with severe feedstocks. More or less the same design principles get applied over here.
And more people asking about limits. Is there a limitation on the percent of pyrolysis oil in the naphtha feed to the steam cracker?
So that's a good question, and there is no fixed answer to this question again, for the simple reason it depends a lot upon the cracker type. As I mentioned in my presentation, there are some crackers which can only accept endpoints as high as 200 degrees C. In that case, the amount of pyrolysis oil that can be co-processed would be quite less. However, there are crackers which can go as high as 350 to 400 degrees C. In that case, a lot of these pyrolysis oils can be co-processed. Another important point is the PONA of these pyrolysis oils. As we all know, most of the cracker operators, they like to have more paraffins in the feed because they have higher olefin yields. Now, if you're producing a pyrolysis oil coming from mixed plastics of a different nature, for example, more on the aromatic side, like more polystyrene, then less of these pyrolysis oils can qualify as cracker feedstock. However, if you use low density or high density polyolefins, then a lot of that pyrolysis oil, because of its composition, can be used as a cracker feedstock. So there is no fixed answer to this question. It depends case by case basis. But having said that, we are seeing a very strong appetite in the industry right now to consume these pyrolysis oils for this application.
All right. Certainly everybody's concerned these days about CO2 footprints. Do we have any information about CO2 footprint of depolymerization process? Does it tend to be higher than standard crude processing?
So the CO2, as this was again mentioned in one of the slides, So CO2 footprint in general, not even on the depolymerization, but looking into a much bigger picture. In chemical recycling, it is claimed that there is reduction of CO2 footprint. And these claims have been made on the basis of some strong and verified studies that have been done by different industry champions. However, one needs to take into account the CO2 savings that come from eliminating the incineration savings. So, and further, more than that, at no federal level or at no legislative level, it has been put out there that these many CO2 credits can be given if a chemical recycling approach is being practiced. For example, very recently in the US, approximately 1 or 2 months ago, there was a big controversy or a big uproar about a bill that has been introduced at the government level, where the chemical recycling products are still not being labeled as recycled, at least for the next 3 years. The government is still evaluating. So there is no set in the stone CO2 footprint reduction by chemical recycling. I mean, however, there are claims that it can be done. That's the answer.
Okay. Going back to catalyst again, on max flux, do you know what the typical run length would be for a max flux catalyst?
So the run length typically would be around 3 years. But having said that, as one can imagine, the run length also depends upon the kind of catalyst poisons or contaminants that are present in the feed. But we project at least 3 years for this application.
And how do you change the catalyst if it gets poisoned?
So catalyst changeout is done pretty much in the same standard way, which is done in conventional hydrotreating units.
All right. Let's see. I think we talked about this in terms of impact on equipment. I just want to make sure because somebody was asking about potential corrosion issues downstream, like HCl.
I presume the question is more with respect to the use of or the presence of chlorine for the max flux process. So most of the chlorine in the feed, typically in these pyrolysis oils, is in the organic form. I mean, there's still some inorganic form of chlorine still left over, and the chlorine goes the same route which it goes in a conventional hydrotreating. If you have nitrogen present in the field, then the chlorine, then eventually you will have the formation of ammonium chloride salts, which can be which are which are water washed away before before the cooler downstream of the reactor. It's the same design measures which one would employ for chlorine mitigation in conventional hydrotreating. The same design measures would go over here, be it in the form of water washing, be it in the form of change of metallurgy. The same concept applies.
Okay, here's a question. I'm not quite sure what the person's going for. I'm going to see if you can figure it out, Rahul. It's just asking, what's the typical size of a max flux hydrotreating process? I'm not sure what size is referring to in this case.
Possibly the question is coming from the fact that in plastics recycling, the throughputs are quite less as compared to what we see in refining and petrochemical segments. Over here, if one talks about 1,000 barrels per day of a plastics pyrolysis facility, it automatically gets ranked in the top 5 recycling categories in the world, while 1,000 barrels per day is nothing for refinery or petrochemical units. So the question is more about whether hydrotreating can be made economical at these small scales. So this is a projection based on our analysis in this industry. We can make max flux economical for scales starting anywhere from 60 tons per day or 70 tons per day of mixed plastics. And one of the main reasons it can be made economical at even these small scales is because of the projected capital savings it brings to the table just because of its unique process concept.
Let's see. Continuing on, have you heard of any revamps of existing hydrotreaters to pyrolysis?
So the co-processing in existing hydrotreating is being strongly looked into, and the reasons are quite obvious. There have been there have been reports as well as news that certain pyrolysis oils, to a certain extent, are being co-processed in existing hydrotreaters on the refinery side.
Okay. Couple of questions about type of content, typical sulfur content, and then a question about can you handle large amounts of biogenic content that's in mixed plastics?
So with regards to the sulfur content, again, there can be no number given as a typical number. It depends a lot upon the kind of mixed plastics that have been used for the pyrolysis process. They actually dictate the levels of and the nature of the contaminant that are seen in these pyrolysis oils. Now, having said that, depending upon how much sulfur-containing plastics were upstream, we have seen pyrolysis oils which can be as low as 100 ppm, and they can go as high as 1500 ppm in total sulfur content. But that doesn't pose any issues for the max flux hydrotreating process. Regarding the biogenic content, if the biogenic content is on the higher side, then we do some tweaks in the max flux process configuration to accommodate that biogenic content. In some cases, the oxygenate set level can be really high, and this is what we see for in the case of tire pyrolysis. And special measures are taken into account to deal with the water that we found downstream.
All right, a question about facility location. Would pyrolysis facilities be located close to downstream plants like refineries or crackers?
So presently, we are seeing two different business models shaping up in the market. One is the decentralized, and this is where the pyrolysis facilities are located far away. And then in the centralized, where the pyrolysis facilities are located on one end, and then all the pyrolysis oils is collected and sent to a common purification or upgradation facility. Invariably, this is our belief that the pyrolysis facilities will always be located close to the waste source. This is because of the logistics involved for getting the waste feedstock. The business model, which would eventually, in our opinion, gain more maturity, is the centralized model, where different pyrolysis facilities are located close to the waste source, and the pyrolysis oil is purified or upgraded at a central location, either close to a refinery or close to a cracker.
The cost of recycled plastics is always higher than virgin, so why should a compounder buy recycled plastic? Virgin is cheap and plentiful.
That's a good and interesting question. And the main reasons it would be the recycling commitments which have been made by the brand owners. Like this was highlighted earlier in one of my slides. We are seeing push both at the legislative level as well as at the brand owner level. Now, those commitments which have been placed by these brand owners would require the compounders to have more recycled material. And that eventually would lead to a market structure where the recycled polymer would start to command a premium over the virgin polymer. A classic example is PET. If one looks at the PET market structure, recycled PET now commands a higher premium as compared to the virgin PET. So that market structure for PET is more developed. For the other categories, it's still in an infancy stage, and it will take some time for that structure to develop.
Nikolai wants to know, is there a preferred technology to process plastics? Thinking about solvent process or pyrolysis as an example.
So both have, there are such no preferred technology. Both have their own pros and cons. The solvent-based processes, they work. And in fact, people have produced solvent recycled polymers. However, there is limitation to the feedstock that can be processed and the intended application of the recycled polymer. In almost all of the cases, the recycled polymer from solvent recycling cannot qualify for food grade. However, there are exceptions. There have been, with regards to polystyrene, there have been recent announcement that recycled polystyrene has been produced by the solvent route, and it can qualify for some of the stringent applications. But we believe the feedstock limitation applies over there. In case of pyrolysis, the main advantage one gets to the table is a more neutrality towards the feedstock. And secondly, since you're breaking that polymer into the building blocks of hydrocarbon molecules, those molecules can be reconverted into plastics, and you can rival the same properties which you get from virgin plastics. So each has its own pros and cons. On the pyrolysis side, of course, you would have more capital investment.
All right, Daria is looking at finding pure styrene monomers from pyrolysis of polystyrene. Is there an expected or a standard yield?
So let's break that question into two parts. So let's talk about the yield, starting from the waste polystyrene all the way to the crude styrene oil, not the final styrene monomer. So that yield is anywhere from 50% to 70%, depending upon which kind of pyrolysis technology you're looking at. Now, from that crude styrene oil all the way to the final styrene monomer, the recovery can be upwards of 96 or 97%. So with these two numbers, the overall yield of the process can be evaluated, and it fluctuates basically depending upon the pyrolysis process.
All right. Is the pyrolysis part of the GTB portfolio, asks Giuseppe.
Pyrolysis is not part of the GTB portfolio.
You're a man of few words. Is it possible to co-process pyrolysis oil in a conventional oil refinery unit?
Yes, it is possible, and this is what we talked about in the second last slide with regards to the valorization. These you get significant advantage because you leverage upon a lot of existing infrastructure, bottom of barrel units, and especially FCC, because in FCC you are actually sort of establishing a circularity because you're producing light olefins. You also produce light olefins from the FCC apart from the gasoline and other products. So yes, the co-processing can be done in the refinery units. However, certain design considerations definitely need to be taken into account with regards to the contaminants that are present in these pyrolysis oils and the PONA or the composition of these pyrolysis oils, and how does that affect the overall performance of the unit.
Okay, Saad is asking about decreasing electricity. I think that's, how do you decrease electricity usage?
So I presume this question is coming more from the perspective of max flux, where we talked about operating expense savings. The electricity reduction is primarily because of the fact that in conventional trickle bed system, you have the recycled gas compressor, and because you're doing vapor compression, the electricity consumption is more. In max flux, you don't have any vapor recycle, you have liquid recycle. So it's liquid compression, and that's where the main electricity advantage is coming from.
Okay, question about gasification. Where does that come into play? Is pyrolysis competitive or complementary?
So pyrolysis is an alternative to gasification. Gasification is a separate technology on its own, wherein the plastics are gasified either in presence of steam or oxygen. You produce syngas. From syngas, you can establish a sort of circularity because one route can be from syngas, you go to methanol, and methanol to olefins. However, there are pros and cons with the gasification approach. The capital investments are relatively higher. And to our knowledge, till date, there is no commercial unit operating on plastics gasification except for one demo plant in Canada. Pyrolysis, on the other hand, is more established, has gained relatively more commercial maturity, and already some pyrolysis facilities have come into operation.
Okay, great. Can scavengers absorbent help upgrade and purify pyrolysis oils rather than hydrotreating?
Yes, in principle, they can purify and upgrade these pyrolysis oils, but there are two important things to take into account over there. Number one, these solutions would only be applicable for small scales. As you go larger, the solution won't be economical. Number two, the robustness will not be there. As one can understand, most of the contaminants in the pyrolysis oils, they come from the mixed plastics. If the mixed plastics quality is varying, the contamination level can go high, which can render these solutions ineffective. The second important consideration is by using scavengers or adsolvents, you don't affect the PONA or the composition of the oils. With hydrotreating, you can affect that PONA. For example, if you have a lot of olefins present in that plastic pyrolysis oils, then they will be invariably saturated to paraffins, which is a preferred feedstock for any cracker. So it can be done, but there are limitations.
Very good. Let's see. We have questions about regulatory frameworks. Does the current regulatory framework support chemical recycling? And there was a follow-up on that. Can GHG emissions be achieved claiming decarbonization?
So regarding the current regulatory framework, although there have been announcements and some decisions being taken, it's still a very foggy area. I mean, there is still a lot that needs to be done, and predominantly I will talk about two different geographies. If you look at the European continent, the activities and from the legislative side are more being adopted over there. As was talked in my slide, they introduced the first plastic tax on non-recycled basis. However, even in that scenario, it's still not clear how the tax should be implemented. Every member country has been left to their own choice as to what mechanism they will choose. In the US, as most of the audience would have noticed, there was a big uproar about a certain recycling bill that was introduced 2 or 3 months ago by two different senators. And as per that bill, it's still being considered whether the products that are obtained from chemical recycling can be labeled recycled or not. And unless until you cannot label them recycled, you cannot collect the premium from such products. The other controversy with that bill was for the next 3 years, permitting is not allowed or has been put on the table to be not allowed for such chemical recycling facilities, unless until a federal body decides whether these facilities do bring in environmental benefits. So, as I said, the legislative area is still hazy, but steps are being taken. With regards to decarbonization, as was mentioned earlier in my slide, again, it has not been set in stone by any legislative body. However, there have been reports and studies by organizations which claim that it does bring in greenhouse gas savings, provided the savings which come from not from the eliminating the incineration are taken into account.
All right. Jorge is asking if you can elaborate a little more about what kind of plastic waste pretreatment is required for the pyrolysis process.
So in the pyrolysis process, as I talked about, we are quite the process is quite accommodating with regards to the feedstock. However, you still need to take into account that certain plastics don't exceed the level in the feedstock. A classic example is PVC. The PVC leads to the high levels of chlorine in the downstream pyrolysis oil. So care needs to be taken on the sorting side of that.
And I think going right along with that, we have a question about if you're picking up plastics, often that's mixed with other materials. You've got metals, foods. How sensitive are solvent methods to those kinds of contaminants?
So solvent-based methods, they are definitely sensitive to those contaminants, but the technology has evolved to a certain extent that when you are trying to dissolve that waste plastics, you dissolve those contaminants and additives, and then you can employ downstream phase separation, mainly phase separation-based methods to remove those additives or contaminants. But there is an extent to which that can be achieved. And that extent is one of the main reasons why solvent-based recycling is not able, in generally speaking, not able to qualify the recycled polymer for food grade applications.
Okay. Well, I am looking at our audience, and they are telling me by the fact that people are starting to drift away that it's time for them to get their papers together and get a cup of coffee before their next meeting. So I'm going to go ahead and close down our session. PTQ Magazine and Digital Refining hope that you found this webinar useful and informational. we would really appreciate it if you could take a moment to give us your feedback on that webinar survey that you'll see when we end the webinar. We will make sure to include a link to the survey in our follow-up email as well. On behalf of Sulfur and Rahul, thank you and enjoy the rest of your day.